Okay, so I'm going to talk today about thermal relativity and how thermal relativity will help us to find out the corrections to the black hole entropy. I also will talk a little bit about Born's reciprocal relativity theory and its connection to quantum gravity. So if I go too fast, please stop me and and ask me to slow down, because sometimes I tend to go very fast. Okay. So the contents, I'm going to, since Fang has to leave earlier, I'm going to probably won't be able to go into very details. But essentially, I want to discuss a little bit about what Born's reciprocal relativity theory is, and how from there we can jump to the notion of thermal relativity theory. And because if we believe in thermal relativity theory, then we'll be able to find the corrections to the black hole entropies, for example, to the Schwarzschild black hole, to the Reissner-Nordstrom black hole, or the Kerr-Newman black hole. And how will that impact in the formulation of a quantum gravitational theory? In particular, the notion of a minimal area and minimal mass, and how that is also related to the Young-Mills mass gap, the information paradox, the arrow of time, dark matter, dark energy. And for me, the most important conclusion of this talk will be the space-time-matter unification. Remember, the essence of Einstein's relativity theory was that he was able to unify space with time. And from that formulation of relativity, he was able to show that mass was equivalent to energy and vice versa. So here I'm going to talk about a space-time-matter unity, where matter can be converted into space-time quanta and vice versa. Now, by quantum gravity here, I don't mean a quantization in space-time. I'm talking about the quantization of space-time. So I'm going to be talking about the atoms of space-time, and how those atoms can be converted into matter, into mass, and vice versa. So for you guys, probably this will be the most important, because you're looking. Yeah. We are talking about the quantization of space-time, a minimal area, minimal length, minimal time, a bit of space-time, and how that will be can be converted into mass and vice versa. So for you guys, this is probably the most important part. Okay, so let me just briefly. Okay, let me just go. Okay, let's start a little bit with gravity versus thermodynamics. You see, the deep origins of the connection between black holes and thermodynamics is still a mystery. Ever since the work of Bekenstein and Hawking, they realized that black holes had a temperature, they behave like light bodies, and they radiate. So still to this day, as far as I know, nobody has been able to find what is the deep origin between, why is there a connection between gravity of black holes and thermodynamics. So this is still a very deep mystery. Even though the people who work in string theory, I remember many years ago, Buff and Strominger were able to derive the black hole entropy from string theory. By that, they counted the microstates of a certain black hole, and they were able to find the relationship between the string theory. But that's, like I said, that's still a mystery. Yeah.
Did you see that slide that we made in some presentation where we have these three equations with the golden ratio on the right side of the equation, where one is Rovelli's equation, and that equation assumes thermodynamics, general relativity, and quantum mechanics to be true, and then on the right side of the equation, to loop quantum gravity approach in Rovelli's, you get just the golden ratio. And then the other equation is...
I was here when you were filming that.
You saw that.
I was here with David. You were discussing this, I remember.
Yeah, and so you can leave loop quantum gravity and quantum mechanics out of it and follow Davy's equation in a completely different way, where on the right side you just get the golden ratio,
yes,
where you assume only thermodynamics, yes, and general relativity to be true. So when you say there's a deep and unknown connection,
yes,
in some sense, whatever that connection is, yes, it has something deep to do with that number, the golden ratio.
Yeah, well, I mean, I remember when you were giving that lecture, because recently I posted a paper about Hardy's 5 to the 5th entanglement, and the connection between non-locality. We'll talk about that later.
The Lucene-Hardy one, yeah.
Yeah. And also some people who work on black holes found the golden mean when they look at the ratios of the stable orbits. I remember some people in Chile, and you guys were in touch with them, I recall, yeah. But I was there when you were talking about that, when you were filming that. I was actually here, I remember. Okay. Yeah. Okay, so now you see the idea of describing thermodynamics using geometric approaches has a long history. It goes back to Gibbs, So he used geometrical methods in order to explain some connection with thermodynamics. For example, in the 1960s, if I remember, Weinhold used the Hessian of an internal energy. In other words, he wanted to construct the notion of a thermodynamic manifold. In other words, where the fundamental variables in thermodynamics is what he called E, extensive variables, and the connection between the internal energy and a metric. So he wanted to construct the notion of a metric in a thermodynamic space, where now, instead of working with space-time points, instead of working with coordinates and time, he wanted to work with the thermodynamical variables. So E in this case stands for extensive variables, like the volume, like the charge, like the mass is an extensive variable. So he wanted to construct the notion of a metric. It's like trying to construct a metric in an information space. But here, you have constructed a metric in a thermodynamic space. You have a thermodynamical system described by a bunch of variables, and he wanted to describe the notion of a distance. How do you describe the fluctuations in your thermodynamic manifold? So he proposed this notion of a metric. Then Ruppiner, I think he's in Florida, he wanted to describe the notion, again, another metric, but now given in terms of the entropy with respect to the thermodynamic variables, with respect to the extensive variables. And the connection between the Weinhold metric and the Ruppiner metric was given by this relationship. In terms of the units, so they were proportional up to the temperature. Then a few years later, actually in the about 7 years ago, Quevedo in Mexico wanted to construct the notion of what he called Geo Metro Thermodynamics. Again, he also introduces a metric in the configuration space of the thermodynamic equilibrium states, spanned by all the variables. So again, all these metrics are basically, essentially, you have a thermodynamic system, and you want to construct a metric in that thermodynamic space. And so Quevedo, I'm going to just skip briefly. He wanted to go from your thermodynamic space to the notion of thermodynamic space. In other words, he wanted to enlarge his number of degrees of freedom, because he wanted to construct a geometric formalism that was invariant under Lejeune transformations. So I'm going to skip this, but essentially what Quevedo wanted to do is he wanted to enlarge his space of variables in such a way that his geometrical structures were invariant under Lejeune transformations. So don't worry too much about this. The most important thing is coming up. Okay. So I don't know if some of you know that many years ago, Ted Jacobson in Maryland, he showed that the Einstein gravitational equations actually had a thermodynamical interpretation. So here on your left-hand side, you have the Einstein tensor. So this is geometry. And in the right-hand side, you had matter. You see, matter curves space. So he realized that this equation could have an interpretation as a thermodynamical equation of state. In other words, he wanted to view this term here, the entropy, the stress energy tensor, he wanted to view as the flux of heat. So dq, so you can think of dq over here as playing the role of a stress energy tensor, which is the flux of heat, the flux of matter carrying heat. So essentially, dq is the heat flux crossing the horizon, the horizon of a black hole, or the Rindler horizon, for example. When you have an accelerated observer, moving with a uniform acceleration. The observer describes a hyperbola in space-time. And the hyperbola has a bunch of asymptotes, and those asymptotes is what you can view the asymptotes as a horizon. It's very similar to the horizon of a black hole. A horizon essentially is like a boundary of space-time. So you can view this term as the heat flux crossing the horizon. And now the temperature T is related to the Unruh temperature. Unruh found a very important relationship between the temperature and acceleration. In other words, when you have an accelerated observer moving with a uniform acceleration with an inertial vacuum, that observer is going to see a thermal gas of photons. If you have an observer who is in an inertial frame of reference, that observer doesn't see any photons. So for him, he sees a vacuum. A vacuum means the lowest state, and there are no excitations. But if you have an observer that is accelerated with a uniform acceleration with respect to that vacuum, that observer is going to see a radiation, a thermal sea of photons. So the temperature that he sees is going to be proportional to the acceleration. And the Planck constant, of course, this is a quantum effect. And over here you have the Boltzmann constant that has units of entropy and the speed of light. So this is the Unruh temperature. And then, of course, and then the entropy, is the entropy of the horizon. And Robert Walt in Chicago was able to show that the entropy of the horizon is nothing but the conserved neutral charge related to the curvature. So in other words, these geometrical equations admit a thermodynamic interpretation given by this relationship. Okay, so essentially what I want to point is that there's a connection between geometry and thermodynamics. Okay, yeah.
Is it too far off topic to imagine Eric Verlin's thoughts on information and entropy related to gravity here?
Berlin, they wanted to do the entropic gravity, where he was using the holographic prescription. Yeah, it's essentially the same equation, the same idea.
Eric Verlin just rewrote that kind of equation, dq equal to ds, and he exactly followed the same procedures that Phil Jacobson did.
He didn't add anything novel?
Nothing.
Well, the holographic screen.
His interpretation forced that equation, dq equal to ds.
Okay,
but
it arrived from a different direction, but arrived at the same thing.
Yeah, but you need to have a horizon. The idea is the horizon is like a holographic screen. You can think of it, yeah. Is this okay? Okay, let me just continue, yeah. Okay, now I'm going to talk a little bit about Born's reciprocal relativity theory. And why is this important? This is important because I'm going to tie up where acceleration comes into the picture. You see, the Einstein special relativity theory, when he formulated, he basically says that all inertial observers are essentially equivalent. By inertial means all observers moving with a uniform velocity are essentially physically equivalent. So Einstein gave the transformation, how one observer in one frame of reference sees the space-time coordinates transform in another frame of reference. But frame of reference, he meant a person who is moving with a uniform velocity with respect to another observer. Now, Born came up with the notion of reciprocity because he realized that, you see, in quantum mechanics, we play with coordinates and momenta. When we look at the Heisenberg and uncertainty relationship, we look at the commutators of the x operator with the momentum operator. So if we want to build a quantum theory of gravity, the coordinates x and the momenta should be on the same footing. So what Born realized is that in the same way that there is a limit in velocity given by the derivative of the position with respect to the time, by duality, by reciprocity, there should be an analogous equation. If there is a bound on the velocity given by the derivative of the coordinates with respect to the position, with the time, again, force is like the derivative of momentum with respect to time. So if x has a relationship with momentum, then if there is a bound on the velocity, there should be a bound on the force. Okay, is this clear? Because force is the derivative of momentum with respect to time. And if P has a correlation with X, that should be a relationship between the two. So this relativity theory actually, rigorously speaking, is not formulated on your space-time, it's formulated on your cotangent bundle, on your tangent space, which is what Finsler geometry is all about. But I'm not going to talk about Finsler geometry. But essentially think of this idea. Yeah. Okay. Now we know that, for example, in ordinary, special relativity, if you look at a Minkowski interval in 4 dimensions, you have the 3 spatial dimensions, and you have the time. You see, this is this portion here is the Minkowski. I'm sorry.
One question about the maximal force.
Yeah.
So we would like to define a maximal force as related to the speed of light.
No. You have to introduce a new variable,
Okay.
a new fundamental constant, and this is where the minimal area, minimal length comes into the picture.
Does that mean that this might support the varying concept of speed of light or something like this?
No, the variable speed of light is something else. Yeah. Okay, so here, this is the Minkowski interval. You have 3 special coordinates, and this is the time. So now let's introduce the momentum variables. I'm going to introduce the contribution of my momentum along my x variable, the contribution of my momentum along the y variable, the direction, and then the energy. Remember, the energy is like the dual partner to the time. Okay, this is the x position, this is the momentum along the x direction. This is the y coordinate, and this is the momentum along the y coordinate. This is z, and so essentially this interval is an interval in phase space, where now instead of having 4 degrees of freedom, I'm going to have 8 degrees of freedom, because I'm going to double my numbers of degrees of freedom. So I'm going to have I'm working with in phase space. Of course, now you're going to see Einstein, in order to match units, remember, this has units of length. This has units of length. This has units of time. So in order to match units, you need a parameter. You need something of velocity in order to make that this object over here has the same physical dimension as this object over here. So this is where the speed of light comes in general relativity, in special relativity. In order to unify space with time, you need to use a fundamental constant, which is the speed of light. Here, in order to unify, in order to match dimensions, if I want to make sure that all these objects over here have the same dimensions, I need to introduce a new fundamental constant, which is, I call B for Born. Okay, and this is where the maximal force comes into being. Maximal forces are having like a maximal density. I know Rovelli for many years has been saying that the Planck energy density should be like a maximal energy density, So I'm introducing the speed of light, but I'm introducing another fundamental constant here, okay, which B is B for Born, okay. And of course, since you are working in phase space, okay, you have a symplectic form, but it's also invariant. So now remember, in ordinary relativity, I have the Lorentz transformation. This is a Lorentz group that rotates coordinates among each others, and the Lorentz transformation, it leaves invariant the Minkowski interval. But now, because I'm enlarging my variables, I have to enlarge my gauge group. So now the group is going to be my special, this is the pseudo-unitary group. This is the U31 now, because now I'm doubling my numbers of degrees of freedom. So my Lorentz group needs to be enlarged to my SU.
So this U31 is double covering of Lorentz?
No, because no. Essentially what I'm doing is like a complexification, if you want to think of it. Yeah. Okay, so now let's look at the coordinate transformations, Okay, so now let's suppose that in order to make life easier, let's suppose that we only work with one spatial coordinate and one temporal dimension. Let's suppose that we're working with a 2-dimensional world, an x and a time. So I'm only working with an energy and a momentum in order to make life easier, So you can rewrite this expression. You could factor out this piece over here. You could factor it out. You can pull it out. And then what you get when you factor things out, you're going to have this expression over here, where this is the derivative of your momentum, and this is where the maximal force comes into being. Okay. Remember, in ordinary relativity, instead of having an f squared, you have the velocity square, and in order to have a maximum force, you have the speed of light square. You have the famous Lorentz factor, 1 minus b squared divided by c squared. Here, you're going to have the ratio of two proper forces. This is the analog of my Lorentz factor, right? Okay, so now you want to look at what are my coordinate transformations that live invariant this interval. Okay, and the coordinate transformations are not that trivial. I'm going to, okay, essentially what I was saying before is that my new fundamental constant is essentially given by the inverse of the Planck. It's essentially the inverse of the Planck area. Remember, if the Planck scale is my minimal area, you know, 1 over my minimal area is going to give you a bound on my maximal force. So if you have a minimal area given by the Planck area, you're going to have a maximal force, because the smaller this object is, the higher B is. You know, the higher, you know, the smaller this, the higher B. So B is my upper bound on my maximal force. It's related to my Planck area, inversely related, you know, because the smaller the area, the larger the B. So you can construct 4 fundamental constants out of the fundamental parameters of my theory, which is the Planck constant, the speed of light, and my new fundamental constant given by B. So out of these 3 variables, you can construct 4 fundamental physical quantities, which is, this is your Planck time, if you want to think of it. This is my Planck length, this is my Planck momentum, and this is my Planck energy. Okay? So out of these 3 constants, you construct an element of time, an element of length, element of momentum, and an element of energy. These are your quanta you want to think about. And they are given in terms of your fundamental constants, which is the speed of light, the Planck constant, and your maximal proper force. Okay? Okay, okay.
So at the end of the day, this is a rewriting of these constants with an anticipation of incorporating thermodynamics into the picture.
Yeah, acceleration, because I want to incorporate acceleration with temperature. This is what Andrew wanted to do, okay? So let's look at the transformations, okay? Okay, let's look at these transformations. I want to transform my coordinates in such a way that they're going to live invariant my infinitesimal interval in phase space. You know, under Lorentz transformation, the proper time remains invariant. So now under these transformations, my proper time in phase space should remain invariant, you know. So notice that here I'm going to have something which I call my velocity boost rapidity parameter over here. And here I have something which I call my force or acceleration rapidity parameter. Because you see, in ordinary relativity, you only have this contribution over here. You don't have acceleration boost. In ordinary special relativity, you only have uniform velocity transformations. But here, you also have an acceleration boost. And I'm going to give you an example of what an acceleration boost is all about. So here, these are my transformations that live invariant, this interval. Because you see, because now when I perform a generalized transformation, what's going to happen is that all my variables are going to be rotated among each other. They're going to be entangled with each other. Okay, so notice here that my t prime in one frame of reference is given my old t, but it also involves my x and involves my momentum. Here my energy is related to the old energy, the x and the p. So under these transformations, what happens is that the space-time coordinates get mingled with the energy momenta. So the notion of space-time coordinate is also entangled with the notion of energy and momenta. You see, this is something, because this is very not very intuitive.
And they're all part of a gauge group.
Yes, the SU, this one, yeah. Of course, you can enlarge it to U31, yes, in general.
So you can just rotate one to the other, yes, and things go up and down, but stay
constant. What I mean by space-time coordinates, now my space-time coordinates get entangled with energy and momenta. And this is why in this relativity theory, space-time and mass are all interconnected. They're all rotated into each other. So you have an equivalence between space, time, and matter. Okay, that's the mantra, if you want to see. Okay. So now what do I mean by velocity boost? You know, in non-linear relativity, my velocity boost is given by the ratio of my velocity with the speed of light. You know, what happens when the velocity reaches the maximum speed? I get this ratio becomes 1, the hyperbolic tangent becomes 1, and my rapidity parameter is infinite. So when my rapidity parameter is infinite, you know, the hyperbolic tangent of infinity is 1. So it means that the velocity has reached its maximal velocity. What happens when my acceleration rapidity reaches its maximum value? The tangent of infinity, hyperbolic tangent of infinity is, remember, this becomes infinity. The hyperbolic tangent of infinity is 1. It means that the maximal force has reached its maximum value. And by psi, this is my net contribution of my velocity rapidity and my acceleration rapidity. So my transformations are not that trivial anyway. So let's suppose that you have a pure acceleration boost.
But do you have some kind of a maximum bound on E prime and B prime? Or they are not bounded?
I'm sorry.
The E prime and B prime.
The
energy.
The energy. No. The energy, they could be infinite. You know, to accelerate a particle to the speed of light, if it's massive, it'll take an infinite amount of energy.
Because in the metric you define a parameter which is 1 over p square, and this p square is something like a maximum.
Proper. It's like a maximal proper force. It's a maximal proper force. Yeah. The proper force. No, we have to be careful with. You're right. I'm talking about the maximal proper force. Yeah. So there's a bound. But you're right, the energy can be unbounded. Like in non-linear relativity, in order to accelerate a massive particle to the speed of light, it will require an infinite amount of energy. Yeah. The energy becomes infinite, but the velocity is actually, can never attain the speed of light. The time and proper time are not the same. There's a gamma factor. Here you have a force and a proper force. Yes. To answer your question, let me go back. To answer your question. Here, this object over here can be infinity. This can be infinity, but the difference is bounded. Okay? Yeah. Okay. Yeah. Okay, so now I gave you a bunch of transformations before. Notice that in ordinary special relativity, under Lorentz transformations, this portion over here remains invariant, and also this portion remains invariant in ordinary Lorentz transformation. Here, this will not remain invariant, this will not remain invariant, but the sum, the whole combination will remain invariant. Okay. So let me just go over here. This is only the combination remains invariant under this generalized transformation. Okay, so I'm going to give you an example. What is the most famous example of what I mean by a force acceleration boost? What do you think is the most famous example of an acceleration boost? You know, let me give you an example. Let me give you a hint. All of us on this Earth, the 7 billion people on Earth, every day at all moments we're experiencing an acceleration boost. Right now, because we are not in an inertial frame of reference. Now the chair is exerting the force on you. When I'm standing up, the floor is exerting the force on me. We are not in an inertial frame of reference. We are all experiencing an acceleration boost.
Because it keeps changing, right?
It's very small because we don't notice it, but in reality, we all, in other words, in order to be in an inertial frame of reference, this is what Einstein told us, that we have to be in free fall. If I drop an object, or a person is in free fall, that person is really in an inertial frame of reference. For example, if I throw an apple at you, or an orange, the trajectory will be a parabola. And the reason it's curved is because neither one of you is living in an inertial frame of reference. If you were to jump in the air, you will be falling with the apple, and when you look at the apple will describe a straight line. The apple, according to an inertial frame of reference, has to follow a geodesic. It will follow a straight line. but because we are not in an inertial frame of reference, we see the curve. So we are all experiencing a force boost. Okay. Of course, it's not very intuitive, but we all right now. Okay. Of course, the force we experience is very small. It's really it's by our weight, you know. Okay. So now, finally, one last thing I wanted to mention is that those transformations that I gave you before, there's another symmetry transformation, which is related to the notion of T-duality in string theory. The above transformations that I gave you, there's a certain invariance under these discrete transformations. Under these discrete transformations, that interval in phase space remains invariant, which is also related to the notion of T-duality in string theory. I don't have that much time to talk about it, but the notion of duality in string theory is very, very important. I don't have that much time to talk about that, but essentially is that those transformations that I gave you also exhibit these discrete symmetry transformations, which is related to the notion of T-duality in string theory, which is a duality between a large and small tension, between a large and small scale. You can think of the minimal Planck scale as being dual to the Hubble scale. The cosmological scale, the Hubble scale, is like the large version of the Planck scale. There's a certain duality between the large scale and the small scales. So here you exhibit that large-small duality, you know, what people call ultraviolet infrared entanglement, you know. Okay, let me just go. Okay, so now let me just go, okay. The consequences of Born Reciprocal Relativity Theory. Okay, there are many consequences, but one of them is that because you're now living in phase space, your physics takes place in phase space, not in space-time, but in phase space. Funny things happen, like there's a time delay in the emission and detection of photons. In other words, there's an energy momentum dependent time delay, meaning that the effective velocity of the photons, even though they move at the speed of light, there's a certain energy dependent time delay in the emission and absorption of photons. This is probably related to what you were saying. Yeah. So in other words, the dispersion relations are modified, so the velocity becomes energy dependent, even though the speed of light is constant. But anyway, this is one of the consequences. Another important consequence is you have the notion of relativity of locality. You know, in ordinary relativity, you know, you can think of a point as the intersection of two world lines. They intersect in a point. So that notion seems to be invariant in ordinary relativity with respect to other observer. So the notion in other words, when you have two intersecting world lines in one frame of reference, they intersect at the same point. But here, in this relativity, because you are working in a phase space, you could have that two world lines, they may intersect in one frame of reference, but in another frame of reference, they do not intersect. So this notion of locality becomes relative.
Is there any quantum version of this theory?
Well, the people who work in doubly special relativity, where they form the Poincaré group with quantum groups, the kappa.
Because here is if locality and non-locality could be relative, this means that many non-local properties in quantum mechanics, like entanglement or coherence or this kind of properties, we can understand them locally in the framework.
You could think. You could try to see if entanglement in quantum mechanics may be related to this, to having observers moving in accelerated frame of reference. Yes. But essentially, what I'm saying is that if you have, two cars that crash into each other in one frame of reference, in another frame of reference, they do not intersect at one point. So this is what I mean by relativity of locality. Okay, now relativity of chronology is something also very similar. What one observer will describe as a physical event to be one defined by the intersection of two world lines in his or her future, in an accelerator observers will describe it as the intersection took place in their past. So you have this relativity of chronology. I know you guys been working a lot with time loops also. This is something.
Clocks.
Clocks, yes. Okay. I know that Jack Sarfati and this guy Sutherland in Australia for many, many years has been working in this, this backward causation. Is that the words they use?
Retrocausation.
Retrocausation. Okay. Yeah. So here you have. Okay, so anyway, I can skip this because there's more. Okay, but let me just go. Because Frank has to leave. Another important thing is that mass energy densities are not invariant under these generalized transformations. Let me just go. Let me just go back to the thermal relativity. That you can generalize the special relativistic transformation to these transformations that involve in velocity boost and acceleration boost. When you work with the cotangent space, so when you double your variables from space-time coordinates, you include the energy and momenta. And under those transformations, space-time gets entangled with energy and momenta. That's basically the moral of the story. And of course, you're going to have many new effects that you don't see in ordinary special relativity. So now let me just go present to you what do I mean by thermal relativity. Not so long ago, Zhao in China presented a very beautiful explanation how the group of general coordinate transformations, how the group G of general coordinate transformations on the thermodynamic configuration space, spanned by all the tensor variables, and he wanted to find a connection between the first law of thermodynamics and the invariance under this group of general coordinate transformations. In other words, he wanted to replace find a connection between the thermodynamic variables and the variables in space-time. So in ordinary relativity, we have the proper time, the infinitesimal proper time interval is given by, in 2 dimensions by this relation. This is the time and this is the x displacement. So he wanted to find a correspondence between what will be the correspondence of this relation in the thermodynamic world. So he found that you see x is like an extensive variable, Mass is like an extensive variable. Time is connected to entropy. We all know that the entropy flows, the entropy increases. We know that the arrow of time flows forward, so we know that entropy in any process tends to increase. It's like the arrow of time. So he proposed the notion of a proper entropy. Remember, this is time coordinate, and this is proper time. So he wanted to associate the notion of entropy. He wanted to find something else, and he proposed the notion of proper entropy, which is a new variable. So notice here you have the mass plays the role of the x, the entropy plays the role of the coordinate time, and the proper entropy plays the role of a proper time here. So he wanted to construct the notion of a thermodynamic interval in your thermodynamic configuration space and find the concomitant relationship with space-time. Okay? So what I did recently is I wanted to introduce the notion of a maximal temperature. In the same way that the speed of light is the maximum velocity, I wanted to now, in order to make sense of this correspondence, I wanted to introduce something over here that plays the role of the speed of light, which is the Planck temperature, which is the maximal temperature. It's a postulate, So here, remember, this has unit of mass, entropy times temperature has unit of energy. So in order to match units, I need something of a temperature over here. Here, in order to match unit, Einstein had to introduce the speed of light in order to match units. Otherwise, you could not combine this expression over here with this over here. So essentially, this is just matching physical units.
Does it?
Yeah.
So what happens to this idea here if entropy does not always increase over time? Because I worry about that because information can act as a self-organizing negentropic force, and in complex systems where it's hard to even quantify the information, it's a bit mysterious, like a black box. But as I look around the universe at many systems, I see things tending to self-organize. Like, I don't see closed system boxes of repelling charges that exclude gravity, strong quantum coupling, attractive van der Waals forces, and more complex things than just the simple thought experiment of a low entropy and high entropy section of repelling charges in an abstract closed universe box. So I'm just wondering.
Here, remember, here this T can flow backwards like a positron.
Okay, so it doesn't.
Positron,
it works both ways with negentropy.
Positron, an antiparticle moves backwards in time, but the proper time is all positive definite. What is positive definite is the expression over here on the left. The dt can flow backwards. It doesn't matter. What you want to be positive is the quantity on the left. So what you want to be positive definite is the quantity on the left.
But flowing back...
ds could be negative. Yes, ds could be negative. Yes.
It could be negative. Okay, yes. So in other words, going forward in time...
Backwards, you can go backwards.
But going forward in time, something can decrease in entropy, and this still works.
Yes, this ds could be negative, but the important thing is that the whole combination, this whole sum, is supposed to be positive definite. The whole combination is positive definite, but you're right, ds could be negative. Okay. Yes. So notice that, note the correspondence between the proper entropy and the proper time. Okay, so that the flow, in other words, the proper entropy can always flows with, flows, you want this to be positive definite. So this can be this could be positive definite, but this could be negative definite, it doesn't matter. The important thing is that the whole combination has to be positive definite.
Which means what when you say the whole combination has to be positive?
The proper entropy. The entropy could be negative, but the proper entropy has to be positive. There's a difference between entropy and proper entropy.
I don't understand. What is that?
The difference between coordinate time and proper time. Yeah, Ali could explain it.
That is his new definition. He just would like to make some kind of new definition of entropy. Of proper entropy, like the proper time.
Yeah. Little s is not the same thing as big S. Little s is a new variable. Little s is not the same as big S. You're thinking about the big S variable. This is what you're thinking about entropy.
But can you define in a short way the difference between proper entropy and entropy?
Yeah, this is the same way between the notion of proper time and coordinate time. Okay, proper time is something which is invariant under relativistic transformation, like the proper mass of a particle. It's always a relativistic invariant. The proper clock, the proper time is always invariant with respect to any observer. The coordinate time is the thing that is not invariant under different observers.
So in other words, there's a notion of entropy that's non-relativistic. That's absolute.
Yeah, and this little s
is absolute, whereas big S is relativistic.
Yes.
So he would like, I think, his idea to define proper time. Yeah. So the proper entropy. The proper time comes from defining the metric itself. Under Lorentz transformation, the metric does not change, which is ds squared. Does not change whatever you make any kind of transformation. From this metric, we define the proper time, which also does not change. As you move, your own time does not change for yourself. You have your own time. That's your proper time. So what he is suggesting, also you have your own proper entropy, which is measured by yourself, not measured by any observer.
Understood, but does proper entropy need to increase over time?
Yes. But not capital S. Capital S could decrease. Yeah.
Aren't you worried about the assumption of proper entropy increasing over time in terms of relying too heavily on classic thermodynamics, which never anticipated strong quantum correlations, nor gravity, nor information like DNA, self-organizing system? Meaning, I worry that very old idea from the 1800s was not...
New. No, I'm adding something new. Okay. I'm introducing the concept of proper entropy, which is something new.
Okay.
The idea here, the entropies that he has, which is big S, could increase or decrease. It's quite relative right now related to the observer.
Yeah, but I'm trying to get my mind, I'm kind of getting my mind around the proper entropy, but still not, which I have my mind around it, which is just, it's an absolute notion like proper time, but I still am having a hard time, from what I understand the word entropy means, whether proper or regular, it means that a system tends to homogenize, right, over time, in the same way that a system of repelling charges will homogenize over time, and that doesn't seem
Homogenize or thermalize.
But this is not the way the universe appears to behave. The universe behaves according to how attractive forces and strong quantum couplings and information, pure information, tend to.
Let me give another example. Imagine you live inside your light cone. You cannot send signals faster than light, so you live inside your light cone. So that means that the proper time is greater or at maximum 0. A photon, the proper time of a photon is 0 because it lives at the boundary of the light cone. But you live inside your own light cone, so your proper time is something which is greater than 0. This quantity square is greater than 0. So this is something similar. Think of it as the differential of S square. This interval has always to be greater or equal to 0 at the very most. It's like being inside your light cone. It has to do with causality. Think of this growth of proper time as the implementation of causality in ordinary relativity.
Proper time, not proper entropy. Maybe Marcelo has an insight that can help me.
This is very important because from here you can deduce everything.
So from my understanding, you have a geometric description of a thermodynamic system, and on the other side you have a description of space-time in the phase space.
Yes.
So you match this. I think the key point is that there are some regimes where you can have a break of a Lorentz symmetry. So we would expect that break in your new derivation.
Yes. When I go to the quantum world, yes. Okay, but then I'm going to the quantum
macro
world.
Scale systems, though. Many examples, but what do you?
I want to help you a little bit. So what Klee is saying is basically, so his definition of entropy has to do with the degree of organization of systems. So in Klee's model of entropy, because the system becomes more and more organized, you have planets and then the solar system and planets and then people and then DNA and then societies and so on. You have a lower entropy system, but you're talking about the entropy at the level of the universe, which is because it's a universe that produces actually entropy. In order to lower it in some cases is actually increasing over time. So I think that's the difference in between what you're saying when you say that the universe tends to self-organize, thus locally lowering entropy. But what Carlos is speaking about is like how you measure the entropy evolution from the beginning of the universe with time, and that is increasing if you go in this arrow of time direction.
I guess what I'm saying is that clearly the universe at some very early abstract stage could be imagined to be in some state of entropy, and then it explodes in a Big Bang idea. But I'm still not convinced that local lowering of entropy is somehow traded off for some other increase in entropy somewhere else, where the net result of entropy in the universe as a whole is increasing. And the reason is because I so deeply distrust this Boltzmann model that relied on a thought experiment of repelling charges in a closed system, because the whole thought concept and these assumptions, which became practically axioms for so many people, did not contemplate Newton's gravity. It didn't contemplate strong quantum correlations, and all of these things that tend to cause a system to self-organize under its own power, toward its own energy, toward greater and greater states of self-organization, which equals greater and greater states of lower entropy. This,
Because I remember, okay, there are two things I would like to say. One thing, there's a fundamental difference between the microscopic arrow of time and the macroscopic arrow of time.
I understand.
And then Prigogine, for many, many years, he spent most of his life studying what you call thermodynamics, non-equilibrium thermodynamics. So there's a fundamental difference between equilibrium thermodynamics and non-equilibrium thermodynamics. Oh, yeah. So I think what you are focusing is in non-equilibrium thermodynamics.
Well, what I'm making is a more grand statement to say that yes, it's easy for any two people to agree that locally entropy can increase. It's not so easy to agree or disagree that between people that globally there must be an arrow. I connect an arrow, I have a better arrow of universal time, which is the expansion of the universe, right? That's a more absolute thing.
Yeah, but then again, the problem that you encounter is not necessarily with Boltzmann because it doesn't include quantum mechanics and all these other effects. The problem is when you have a system that's closed or open or expanding and so on. And as you were saying, that's a non-equilibrium system, and we don't know, besides that, we don't know that. We also don't know if we can treat the universe as a closed system or as an open system. So this is where you have problems.
Dissipation also.
And the other problem I have, or concern, is, I'll let your next, the other concern I have is that the more and more I study it and think about it, the more profound complex emergent information, abstract information seems to play on compelling, in influencing systems under the power of their own intrinsic energy to self-organize toward higher negentropic states.
Yeah, but that sometimes uses, just a second, Richard, that sometimes uses very high entropy processes. Mm-hmm. Like, think about it, like, for example, if you have, in order to form planets and whatever, you need high energy supernova explosions and all this other stuff, which are like, if you measure the energy and the entropy, that's kind of like a huge entropy production, but then you do it, if you think about causality, in order to form stuff that you can organize.
Yeah, it's just so hard to experimentally validate because you can't experimentally observe very large systems.
What is Richard?
Richard.
I'm sorry. Richard, what were you going to do?
So Carlos has some notions based originally on the standard concepts of entropy and then on certain modifications that he's talking about. If Klee and if the QGR model has disagreements or different ideas about the standard concepts of entropy, now in the middle of Carlos's talk is not the time to try to hash that out because we've already spent 10 minutes talking about it, and we could spend 2 days talking about it. Let's just let Carlos finish his talk.
I'm going to give you, remember when you guys went to Santa Barbara, remember Susskind? I'm talking about complexity. The growth of complexity. You have complexity and uncomplexity. Right. I remember Susskind spent a lot of time. We could talk about Suskind's work later. Right. Okay, because complexity, what is different. Remember that in his lectures he emphasized that we must not confuse the different notions of entropy and what he meant by complexity and uncomplexity. Remember his lectures at UCSB? Yeah, okay, so we could go back to Susskind, okay. So let me just, let me say, I have this interval over here. So what I'm going to do is I'm going to factor this first term, I'm going to factor it out. And like you do in ordinary relativity. So when you factor out, you get this. I haven't done anything. I had just factored out the first term outside. I have this parenthesis. So notice when I take the square root on both sides, what do I get? I get my proper entropy is given by, in terms, it's proportional to the total, to the proper entropy. And here I have something that looks like a Lorentz factor, remember? Well, the inverse Lorentz factor. So now, when I play a little bit with the algebra, from this equation. It's just basic algebra. So what I hear is that my differential element of mass, is proportional to my proper entropy. And right over here, I have something that looks like a Lorentz factor. Remember, 1 over the square root of b squared divided by c squared. So temperature is like a b squared. This is my maximal temperature, it's like c squared. So this is like a Lorentzian factor. So this will be my thermal relativistic correction to my black hole entropy. So I'm going to use this formula to evaluate my corrections to the ordinary Bekenstein-Hawking entropy.
This even will correct the metric of black hole itself.
I'm sorry?
This will correct the metric of the black hole.
Yes. So here, I used U because I was thinking of unrolled temperature, but think of this anything. So here I have the analog. Remember, this is the analog of the Lorentz dilation factor in non-inertial relativity. So here I have my thermal Lorentzian factor, my analog of relativity. So remember that my temperature can never attain my maximal temperature because otherwise you will get an imaginary value. You'll have like a tachyon, you know. So here, this Lorentzian factor can go from 1 to infinity as my temperature goes from 0 to infinity. I'm working here with absolute temperature. I'm talking about in kelvins, you know. Okay, so now you can do the same thing with phase space. You know, you can do the same analogy when you go from my thermodynamic configuration space to my thermodynamic phase space, and you can make it even more complicated where you have the analog of a force. You have a thermal relativistic force. So I'm just going to skip this for the moment, and I'm just going to the nitty-gritty of the talk. And then, of course, my first law of thermodynamics in phase space, you have to work in your thermodynamic phase space. So anyways, you have a similar relationship. But anyway, let me just go to the, this is my thermal analog of my Lorentz factor. Okay. So now let's replace now, let's go now to Hawking. I'm going to claim, let's see what happens when I replace my temperature here with my Hawking temperature for black holes. Okay, so I'm going to find my corrections to the black hole entropy, my thermal relativistic corrections when I replace T for my Hawking temperature. And let's see what we get. Okay, let's see. Okay, so remember the way Hawking derived the temperature for a Schwarzschild black hole. Remember, this looks like the Unruh relationship between temperature and acceleration. I'm working with a system of units where H bar, C and the Boltzmann constant are all equal to 1, you know, to make life easier. All those constants are set to 1. So here you take the derivative of the temporal component of the metric with respect to the R, and you evaluate it at the horizon. Remember, the Schwarzschild horizon of a black hole is at 2 GM. So when you do the algebra, you know, when you take the Schwarzschild metric, the temporal component, you do the algebra, you evaluate at the horizon, you end up with the Hawking's famous formula. Now, the Hawking temperature really is the Hawking Unruh temperature. It's inversely proportional to the mass. So you see, when the black hole begins to evaporate, what happens is it loses mass. And as it loses mass, it begins to get hotter and hotter and hotter. In other words, it's an unstable system. And that's why it explodes.
Catastrophic behavior of the black hole because the temperature will go to infinity.
Yeah, it has negative specific heat. So it's really unstable. But anyway, don't worry about the instability of the black hole right now. So I'm just going to use this formula. And I'm going to include this temperature given in terms of the mass. And I'm going to insert this value in my Lorentz factor, or the inverse of my Lorentz factor. So in this way, I'm going to find my corrections to the black hole entropy. So in other words, I'm going to have, remember here, tilde S is my proper entropy divided by my Planck temperature. So, because you know, you always have to be careful with the units. You make sure that the units, you always have the right units. So by tilde S, I mean my proper entropy divided by my Planck temperature. So I'm going to evaluate how does my entropy depend on the mass. Remember, here, this is mass here. I have a mass here over here. Remember, the temperature is inversely proportional to the mass. So what I'm going to do is I'm going to perform this integral. I'm going to evaluate this integral. And because you have these relativistic thermal corrections, you're going to have a bound on your lower mass. The bound on your lower mass is related to your bound on your minimal area, your minimal length. So what happens is that the black hole is going to evaporate, but not forever. It will not reach mass 0. it will, once it reaches its minimum mass, is what you call a black hole remnant, it will stop evaporating.
But is this remnant still have some kind of, is it normal matter or?
No, here we'll talk about dark matter in a minute. So okay, let's do this integral. So when we do this integral, anyway, if I'm not, you do this integral, if I hope I did it right. Anyway, so this is the indefinite integral. It looks a little bit ugly. Okay, so at the very end, when you do the integral, this is what you get. You're going to have that the corrections to your entropy, and I'm going to tell you what the S sub naught, this is the minimal entropy, is very important. The minimal entropy, it will happen to be 0 associated with the minimal area. The minimal area will have entropy 0. And as you increase your area relative to the Planck area, the entropy will increase. Remember, this is the expression from doing the integral. So you're having, so all of you will recognize A divided by 4G. This is the famous Bekenstein-Hawking entropy. But here, due to the thermal relativistic corrections, you're going to have corrections to the ordinary Bekenstein-Hawking formula. So you're going to have a correction of this that looks like this, and you have logarithmic corrections. Okay? So this expression looks a little bit ugly. You know, let's suppose that the area you want to have you want to look at the entropy of a black hole associated with with the mass of the sun, or 3 solar masses, or the nucleus at the center of the galaxy. Anyway, so you can let's expand this square root in a Taylor series. So you can rewrite this formula for very large areas, compared to the Planck area. So when you expand it, because remember, this is the original entropy of Hawking. So when you do the expansion, okay, let me just, and then I'll go back to this. Okay, let me go back. This is what you get. You see, the first term is the ordinary Hawking-Bekenstein entropy. Then you have a correction given by this term over here, and then you have corrections in powers of the area to inverse powers. Okay, and then you have these logarithmic terms. So you have, okay. But remember, the exact formula is this one. This is the exact formula. This is the exact formula. So what's going to happen? You're going to see immediately that you want to make sure that this square root, doesn't give you an imaginary number. Okay, so you want to make sure that this number over here does not exceed 1. Okay, and this is why you're going to have a minimal area. The minimal area is given when with this expression over here is 0. It's when you reach the speed of light, the Lorentz factor becomes infinite. So this is something very similar. There's a bound on the area because you don't want this expression to be imaginary. You don't want the entropy to be an imaginary number.
Does this minimal area correlate to the transition or the phase transition of the specific heat from positive to negative?
Here, yes, somebody was saying something? No, here you're going to have a phase transition, but I think what happens is that space-time becomes fractal. It's a fractal space-time. So the phase transition really, this is what I think, is that space-time becomes fractal.
But in the black hole, when the specific heat phase transition occurs from positive to negative specific heat, does it? I wonder how that. So that would correlate to the size of the black hole, because as it radiates, it'll get smaller, and then there's this one point which should relate to a diameter or a radius that gets you to that one moment where it flips from positive to negative.
Well, here you can never flip because you reach the minimal area. It's like you can never reach the speed of light. You will reach the speed of light asymptotically. It will take you an infinite amount of time to reach that point. So here, you have also this time dilation effect that everything will freeze.
Because the reason I ask is just abstractly, even if it's like an electron at rest, even if it's not a physically realistic idea, it's I find it very intriguing that without any use of the Emersi parameter or any notions of LQG, that in Davy's equation, just assuming entropic theory and general relativity, that golden ratio comes up at this point where the black hole abstractly, right, transitions, right, from its specific heat from positive to negative. That's where that...
You're talking about the Mirizzi parameter?
No, in that slide that you remember, it was the Rovelli equation at the bottom, and it's really interesting because that phase transition from the positive-negative specific heat phase transition is going to be relative to the radiative sort of reduction in radius of the black hole. And since you're tying this into
okay. Because I think the work of Rovelli and Ashtaker and company, they also assume that the Planck energy density is the maximal energy density. So what happens in loop quantum gravity, you're going to have what they call a bounce. So the black hole tunnels into a white hole.
Right.
So what happens?
But Davies doesn't anticipate anything with LQG. Davies equation is classic. It's just
general. The Paul Davies.
Okay. Yeah. And it relates to that one transition, and then other than that, you don't get the golden ratio. It's only at that one special phase transition from positive to negative, which should relate to the radius, which relates to Hawking radiation reduction.
Here, what happens is that the black hole radiates, but eventually, when it gets smaller, when it reaches the Planck mass, the Planck area, it stops. So it reaches its limited point. Because in that case, space-time, you cannot go smaller than that. Because remember, the atoms of space-time is made out of these atoms, and you cannot go smaller.
And you're saying the specific heat sign value transition cannot occur?
No, in that case, it stops, and you reach the edge, and that's it.
So it never occurs physically in this specific heat?
In this relativity theory, when you include the thermal relativistic corrections, you stop there. It's like what you call a black hole remnant in people who work in gravity.
Well, no, that I agree. I was just wondering if the specific heat transition, as far as you know, is a physically possible state of a black hole.
I'm going to look at the correction to the specific heat. Because here, all the equations that we know from black hole thermodynamics, all the equations need to be modified to include the thermal relativistic correction.
Actually, the specific heat at the bound will equal to 0 because it will stop radiating.
Yes, stop radiating. Yes.
So it will equal 0.
Yeah. So remember, in this theory, when you reach the minimal area, the minimal entropy is 0. Okay. Okay. So let me just go.
The minimal area, you got to 0 entropy.
Yes. Due to the corrections, to the thermal relativistic corrections, it happens that the minimal area has 0 entropy. Yes. When you do the algebra, you'll see that the minimal area has 0 entropy. It's like the 0. I want to see whether or not we have the third law of thermodynamics is modified, because remember, in the third law of thermodynamics, you reach the entropy becomes 0 at 0 absolute temperature.
But you got this initial entropy as 0 by hand or just?
No, the thermal relativity forces you. Thermal relativity forces you to choose. Yeah, because when you set A, okay, let me just go. When you take A to be the minimal area, okay, let me tell you what the minimal area is. You see, when you reach the minimal area, okay, you can show that this is 0. Okay, it's just basic algebra, you know. Yeah, well, basic quote unquote. Anyway, you know, when you talk to Witten, everything is rudimentary, you know. But anyway, okay. So you see, due to these relationships, you can show that the minimum value of mass is the Planck mass divided by 8 pi, is related to the minimal area. You know, you see, and the constant is the corrected entropy associated with the minimal area. And then when you do the algebra, when you plug in the minimal area, you get log of this. But what happens is that this becomes 1. And log of 1 is 0. So when you reach the minimal area, this 0 point entropy is 0. So the entropy becomes 0 when the minimal area is not 0, The minimal area is of the order of the Planck square. So at this area, the entropy becomes 0.
So that's amazing. That means that the geometry here is more fundamental than the information itself. The geometry is more fundamental than the information.
Well, I want to connect information with geometry. This is what I'm trying to do, because for me what I want to do is work with information geometry, and I remember that for many, many years ago, Fisher information and Burs and Hellstrom, there's the notion of information metric that has been floating around for many, many, many years. So what I want to do is try to connect information theory and geometry, try to weave them together. That's what I want to do.
Yeah, I mean, you can connect geometry to number theory, but how is geometry not information? Depends what your definition of information is.
If we define the information as the entropy itself, if the entropy is the information, then you have something here more remnant than the entropy itself,
right, like
which is the minimal area.
Like a Shannon-Boltzmann equivalency idea? Okay.
Yes. The minimal area. Of course, if you set A to be 0, it happens that the entropy becomes imaginary.
Yeah.
You see, so this is why you have to have it's like a tachyon in relativity. This is why you have to have a bound, a cutoff. It's like an ultraviolet cutoff, you know. Okay, so I'm going to pause a little bit because you need to digest this. Okay. Yeah. Okay. So this is when you span in a power series, and in a very large limit, compared to the Planck area, you get this expression. So you have an area, you have a logarithmic correction, and you have these constant terms, you know. So you see, I haven't compared these extra terms. You see, many people have worked with logarithmic corrections to the black hole entropy for many, many years, using loop quantum gravity and string theory. So I need to compare these corrections with the quantum field theory corrections. I haven't compared them, because I hadn't had the time. But I know that people in India and other places have looked at logarithmic corrections to the ordinary black hole entropy. So now, if you follow this procedure, you can also evaluate the corrections to the a charged black hole or a charged rotating black hole. You can follow the same procedure, but now when you have, for example, if you have a Kerr-Newman black hole, you are going to have, in addition to mass, you have angular momentum and you have charge. Okay, so now your physical space has more parameters. You have the mass, you have the angular momentum, and you have the charge. So therefore, your thermodynamic manifold has been enlarged. Your thermodynamical parameters have been enlarged. So now your proper entropy will depend, on the old entropy, the mass, the angular momentum, and the charge. Okay. Remember, capital S, capital M, capital J, capital Q are what you call extensive variables. And the temperature, the angular momentum, the angular velocity, and this is the electrostatic potential. It's what you call an intensive variable. An intensive variable is like the pressure, like the temperature. An extensive variable is something that changes when you double the size, you double the variable. But intensive variables, you don't change the pressure when you cut the room in half. So this will be the proper entropy associated to the mass, angular momentum, and charge of a Kerr-Newman black hole. So and then you follow the same trick before to find what is the thermal correction factor to the mass when you fix the angular momentum and the charge, and then you do the algebra, and then of course you're going to have a very ugly integral, because remember the Hawking temperature associated with a Kerr-Newman black hole is more complicated, because now it depends on the mass, it depends on the charge, and depends on the angular momentum per unit mass. So it has a more ugly expression. It's given by this. And it can be written in terms of the outer and inner horizon, where the outer and inner horizons are like this. And the golden mean is here. The golden mean is here. when you look at certain specific values, yeah. So of course, when you hold the angular momentum and the charge fixed, this will be the thermal relativistic corrections by the gamma factor to the ordinary entropy. Of course, the integral you're going to get is going to be extremely complicated because now you're going to have to do this integral. But now the temperature and the temperature is very, very ugly. It's extremely complicated. So the integral you're going to have is very, very messy. So when you do the integral, you know, in Mathematica, Ray will be very happy to do it. You'll find that the thermal relativistic corrections to the Kerr-Newman entropy. Okay, so it's a very ugly expression. But you still have the same basic idea. You have a minimal area, a minimal mass, and then you have a Hawking evaporation, but it will stop eventually when you reach the ultimate quanta of space-time. Yeah.
Here also,
Yeah.
you might have also a minimum charge, right?
Yes, you have bounds. You'll have bounds because you want to make sure that the charge does not exceed the mass. So you have like a BPS, you know. Yeah, you'll have bounds. Yeah, on the.
So is that the charge you could explain the entropy charge for the electron or something?
Yeah. You could also have magnetic charges if you want to add magnetic charge. You could have dions. You could complicate your life as much as you want. But yes. Okay, so now since Fang has to leave, let me look. What are the other physical findings pertaining to thermal relativity? Okay, so I propose a thermal relativity theory. Okay, what are the consequences, the immediate consequences? Okay, so I just show you that there's a 0 point of entropy where the proper entropy associated with the non-zero area is 0. Okay? I gave you the idea of the notion of your thermal, the analog of your Lorentzian factor. Now it's a thermal Lorentzian factor given by this expression. So notice what happens. You see, when you reach the maximal temperature, you have attained the minimal area, you have attained the minimal mass, and then, of course, this factor explodes. It blows up. You know, when you reach the speed of light, the Lorentz factor blows up. So it tells you this is how far you can go. You know, in this case, instead of going to a larger world, you go to a smaller and smaller world. So it's like a cutoff in your macroscopic world. So of course, the Hawking evaporation will stop, and you leave a black hole remnant of the Planck mass. But remember, the maximum temperature you can reach, it can never surpass the Planck temperature. Once you reach the Planck temperature, the black hole evaporation stops. So the black hole temperature plays your cutoff. You know, it's your maximal temperature. It's like having a maximal density. Then, of course, let's look at the black hole evaporation times. Remember when Hawking told us that if you have, for example, if you have a black hole of the mass of the sun, and then they ask you how long it will take for the sun to evaporate. Imagine the sun was a black hole, which is not. We know it's not because it takes at least 3 solar masses. But let's suppose that the sun, you compress the sun to, 3 kilometers? Is the horizon radius of the sun?
I think 3 kilometers.
Marcelo, remember, if you compress the sun to 3 kilometers, it will become a black hole. I think it's about 3 kilometers. Yeah, you take the sun, you compress it, it becomes denser and denser and denser, and then once it reaches 3 kilometers, it has enough density to be a black hole. It means that the sun lives inside its own horizon. And you let it evaporate. So if you look at this expression over here, you know, essentially this will give you the evaporation time. So essentially you take the mass of the sun, you divide by the Planck mass, and you multiply by the Planck time, and that will give you the evaporation time of the black hole. But remember, now due to this factor, due to the thermal relativistic corrections, the black hole evaporation times are much faster. So what's going to happen? That the black hole is going to evaporate much faster. So what's going to happen at the beginning of the universe? At the beginning of the universe, imagine you have a bunch of primordial black holes. You know, for many, many years, people thought that the source of dark matter and dark energy was due to the primordial black holes. Here, you're going to have an enhancement effect. Due to these thermal relativistic corrections, you have this enhancement of the temperature effect, but also the evaporation times are going to be much, much rapid. So maybe due to this thermal relativistic corrections, you could find an explanation for dark matter and dark energy due to the thermal relativistic corrections.
So this might also, I think, introduce some kind of resolution for the information loss.
Yes, yes, because now I'm going to look at because now what happens is that the thermal Hawking distribution is no longer given by you know, the Bose-Einstein distribution. It's going to have corrections. Yeah, I'm going to move that into a minute. Okay, so the dark matter. So I already explained to you that now, due to these faster evaporation times, so maybe due to these thermal relativistic corrections, maybe you could find some source of dark energy and dark matter. You know, because you're going to have thermal relativistic enhancements to the temperature, but also that the evaporation times are much faster. So if you have a lot of primordial black holes at the beginning of the universe, they are going to evaporate extremely fast, and you may be able to observe them. Yeah, yeah.
So some source of dark matter may be found, but that cannot account for the whole dark matter that we're missing, because I mean we can discuss about this, not to bore some other people for the next few days, but this doesn't work with a lot of observations that we have at the level of galaxies and structure formation. So you can't actually do dark matter with just primordial black holes. The full
No. But once you include the thermal relativistic corrections, all the calculations will be
even
affected.
there. I think you're referring to stuff like cores and whatnot, but with the structure formation and velocity dispersion of galaxies, it doesn't work.
Yes.
But we can discuss about this.
Yeah, but also remember, you also have radiation. These black holes will evaporate much faster, and the effective temperature is going to be much larger, so they will also contribute to the background energy as well. So you may have also some sort of gravitational repulsion as well. Yeah. Okay. Yeah. Okay, so the deviations from pure thermal radiation. This is what Ali was saying, finally. So you see the Bose-Einstein distribution now will receive relativistic corrections now, because you have a correction in your thermal factor now. So you will not have the Bose-Einstein distribution. So what happens is that this will have profound consequences for the black hole information pattern. See you tomorrow. Say hi to the children. Okay. So this is what happens when you reach the Planck temperature. You see, when you reach the Planck temperature, your thermal relativistic factor becomes infinite. The effective beta factor is 0, so this blows up. So what happens is that this will have profound consequences for the black hole information paradox, because now your distribution is not purely thermal. So now pure states are not going to evolve into mixed states. So this is going to affect the information paradox.
With the information paradox, can't the information be encoded in the Hawking radiation?
Here, the Hawking radiation is actually modified, because now you have to modify, it will not be thermal. You see, the problem with the information paradox is that you have a pure quantum state evolves into a mixed state, because this is due when you have a thermal radiation. How do you call it? When you take a thermal average, you have to average over all the thermal states. But here, because you no longer have a pure thermal distribution, then you probably will not have that problem, that a pure state will evolve into a mixed state. So you may bypass that problem.
But what I mean is, irrespective of what you're explaining today, the general problem of the information paradox, just my ignorance, but cannot one make a conjecture that the information that has fallen into a black hole, the quantum information, is encoded in the Hawking radiation?
Yeah, it should be. Yes. You're right. But the encoding process is going to be very, very subtle, because now, in other words, you will no longer have thermal photons. Is that the word to use? So you have to be very careful now with your quantum bits. They are not thermal photons, so the counting is not to the 2 to the n. There will be modifications in the counting of bits.
I think the idea here is about the information loss, that this black hole, when some kind of material is very complicated go inside the black hole, when the black hole make evaporation, the Hawking radiation does not contain anything very useful about the complexity that went inside the black hole.
Well, we don't, I'm just saying, can one conjecture that it does? Meaning, could it, meaning, is it absolute that it cannot?
But the Hawking radiation itself does not contain anything. That is the equation what she is saying. But here what they are proposing, that the remnant itself,
the black hole remnant, because remember,
this kind of complexity is stored there.
You know, I wasn't, but without relating it to this and the black hole remnant, I'm just saying that the Hawking radiation, it also has a gravitational ripple, and I'm just saying in that waveform.
No, you're right. There is information encoded in the radiation, but here, because you have a black hole remnant, the missing information, the information loss, may be encoded in the remnant.
Also could be. It's another way of thinking about it. Yeah.
So the remnant contains that missing piece of information. Yeah.
Because the equation of Hawking radiation itself does not contain anything about what kind of complexity that we had before this object went inside the black hole.
Oh, I know that, but I'm saying it could, meaning and it
Well,
also.
in reality, they are correlations. They are correlations. Yeah, you're right.
The equation of Hawking does not. We don't have equation.
No, that I know, but yeah.
But here, because you have a black hole remnant, that black hole remnant will have a memory effect of what went in. So it has a memory, you know, and it might tell you something about what went in was, I don't know, 1,000 people or 10 people or 5 people or whatever. It will encode some information of what went in the black hole.
I guess it's a deep question that if information is scrambled so intractably that it's very difficult to unscramble it, is the information still there, right? In the radiation, because if a black hole is radiating, it also radiates gravitational ripples, and information can be encoded in that in some complex waveform like that.
So the idea is to look at the radiation that comes out, and also look at the black hole remnant.
Yeah.
And see that
if they sum to the total information.
Yes. Well, rolling quantum gravity, I'm talking about the minimal area, the minimal mass, the maximal temperature, the phase transition of the Planck scale, the arrow of time, and then of course I'm asking these are hypothetical questions. What are the effects that thermal relativity will have on Weinberg's asymptotic safety program in quantum gravity, in Lorentz relativity, in loop quantum gravity, in string theory, Dow special relativity, non-kinetic geometry, blah 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 blah.
Carlos, is this your last slide?
No, I think I have one more.
Okay, after you do the last slide, if there's still any time, I was wondering if you can give an elevator pitch on the essence of Finsler geometry, and if you think it could have any helpfulness for our program.
Yeah, it's very important. Yeah, it's very important. Yeah, but when do you want me to give it?
Well, it's getting kind of late, but during your trip, if
when I come next time, because when I come next time, I would like to talk about the extended relativity theory in Clifford spaces, which Richard would like that, and also about a little bit of Finsler, and I have also some other talks.
Or maybe before you leave on the trip, if you could give a 10-minute essence.
I could, okay.
It's probably impossible.
I need to review it.
Okay, if that's not practical.
This is not special relativity. In fact, it's a generalization to gravity. Uses explicitly Finsler geometry. So,
do you understand Finsler geometry?
Yes.
Because if you do, I can.
Finsler geometry essentially is physics on the tangent space. That's what all called tangent space. That's basically what it is. Instead of working in your 4 manifold, you're working in your 8-dimensional cotangent space. You know, essentially that's what it is. Of course, you need to have a nonlinear connection. You know, and it's more complicated. You know, because the equations are horrendously complicated. Okay. Because you end up having. You have more degrees of freedom, you have the nonlinear connection.
It was very difficult math.
The math is complicated, yes. Okay, now for me, this is the most important, for me, in my opinion. Remember at the beginning when I talked about the mixing of space-time coordinates with energy and momenta in this Born Reciprocal Relativity Theory? For me, what I want to pursue is this space-time-matter unification problem, where the space-time quanta, the atoms of space-time, comprise of closed string loops of minimal area, of the order of the Planck area, can be converted into matter and vice versa. Because you see, in general relativity, there is no local notion of mass. There's no such thing as a local notion of mass. So what happens is that really the mass of a black hole is delocalized and spread across the horizon boundary in terms of your bits. So for me, what I really want to focus is in this idea that the delocalized black hole mass is a condensate of space-time quanta, and is the real source of black hole entropy via entanglement. Yeah. That's what I want to focus on in the future. But and then
I think that's really interesting.
Yeah, and then of course the notion of total relativity. When I was in Atlanta, I spent many hours talking with David Finkelstein about the idea of total relativity, including topological relativity. But anyway, for many years I've been working on the extended relativity theory in Clifford spaces with Mate in Slovenia, where string, membranes, and p-branes are all unified on the same footing. In that way, where your Clifford space contains the vectors, bivectors, trivectors, polyvectors. In Born Reciprocal Relativity or infinite geometry, you work with your maximal speed of light and maximal proper force. In scale relativity, where Notal works with fractal space-time, where the Planck scale and the Hubble scale are the minimal and maximal scales. In doubly special relativity, you deform your Poincaré algebra by working with quantum groups. Thermal relativity. So here, I'm invoking the notion of total relativity. So I think in order to quantize gravity, we have to try to enlarge the concept, the principle of relativity, and try to generalize it to other areas of physics, because I think quantum mechanics and relativity are not enough. We need to tweak quantum mechanics a little bit, and we need to tweak relativity and enlarge them. Yeah. Before we can embrace them, we need to enlarge both relativity and we need to enlarge quantum mechanics.
Right, which is part of the problem of people finding a successful unification. Maybe they both need to be modified before you can see the connection.
Yes. So that's the... And then the references, these are the reference, by Weinhold, Rupiner, Quevedo, Wald, Paddy, by Born, by Brand, Toller. I think this is me. Anyway, Lowe, in Austin, he's the one who wrote down the transformations, And then Notal, Giovanni, and Lukieski, I think this is the end. Anyway, so this completes the talk. Anyway, so I hope it was not too over the top.